Okay, so we did that, and now of reflection, what didn't you see in the plant? And I want to think about this. You didn't see any pumps, right? There were no pumps in all those drawings that I showed you. And there was nothing that looked like this. This is a section from a water treatment plant. And it includes conduits for electrical wires. It includes pneumatic control tubes. Do you guys know what pneumatic control tubes do? Like, how would you? You need a course in automation. So if you want to move a big valve in a water treatment plant, one of the ways of making that big valve open or close is to have a computer that sends a message to close that valve, and that closed valve gets turned into a signal that opens up or closes a little valve that controls air. And then the air goes in a hose, in a tube, up to the actual valve that you want to control, and that air pushes that valve closed or open, whichever way you're going. Okay, so you have software that controls electricity, that controls a little valve, that controls air, that controls a big valve. So in water treatment plants, there are often bundles of these pneumatic control tubes running around the plant to get that automated control. And you didn't see any computers. And that is kind of the motivation for today's class, in that you didn't see all these things. And instead, what we're going to do is we're going to work really, really hard to do all of our controls using hydraulics and like smart fluids. So why are we doing that? It's because computer controlled flows and water levels in water treatment plants cause a lot of problems. They are easier to design, but they're much harder to maintain. They're easier to design because you can just pull existing components off the shelf and say, get this widget from supplier X and put it in this design. But they're much harder to maintain because all of these parts have lots of components that ultimately fail. And here's one of the reasons why I think our design of plants is particularly challenging to think about bringing into the US, where we are extremely risk averse, and where making sure that you are not liable to a lawsuit is like what's on everybody's mind. By using other vendors' parts for every piece of the plant, it enables consultants to pass a design risk or a design error risk off to the vendors. So the vendors are responsible for making sure that their parts actually do, what the consultants specify. And so it's not a part that the consultant is designing. Like, the consultant isn't designing the hydraulics for the flocculator in a certain way to provide the mixing that's necessary. The consultant is putting that design off onto a vendor who provides a mechanized mixer that meets those specifications. It introduces unnecessary complexity, and that complexity ends up getting in the way of successful plant operation because it's more difficult for the operators to diagnose problems. With a complex system like the one I was describing, with electricity and air and valves and computer software all working together, there's so many systems built on top of each other. It's difficult to figure out what's wrong when something is wrong. And there's so many parts. So every time you add these mechanized control systems, each of those has many moving parts and many electrical contacts, all of which are susceptible to fail. And to remember, a water treatment plant is actually not a nice place for electronics or moving parts, because it's wet, it's damp in a water treatment plant all the time. So for all those reasons, we're interested in doing this as much as possible without using those kinds of parts, or at least creating designs that work well, even if they don't have those controls built in. So we use smart physics and fluids. We attempt to create fail-proof designs using smart hydraulic controls. And hopefully we make it a whole lot easier for operators to learn how their plant works. We eliminate almost all of the moving parts, and we design the geometry so that instead of electrical motors moving things, instead of that, we make the water move. So we create the geometry so the water has to move the way we need it to move so that the right things happen. And then essentially we turn our computer code into concrete and PVC. So or rather our implementation partners help with that process. And the operation of the facility is then controlled by how the plant is actually built and how the plastic components are put inside the concrete tanks. So now all of that is to say, we need to know how fluids work. And I know that almost all of you, or maybe all of you, have taken fluids course at OSU. So this is not questioning that, because I do the same thing in previous classes with other students as well, where I feel like I taught fluids for 10 years. And my reflection from all of that was that it would be better if all students took fluids twice, once to kind of begin to learn how it works and maybe bomb out on a few concepts, and then take it again and more of it would begin to make sense. So I know you didn't, most of you presumably did not have the opportunity to take fluids twice. So we'll talk about fluids for at least today and Tuesday to help refresh your memory and maybe make a few concepts a little clearer for you. So we want to talk about drag, we'll talk about head loss, we'll talk about the Bernoulli and the energy equation when we'll have some fun. And this is where I want you to just be bold, and I'm going to ask you questions, and I want you to vote just to, without any more information. I want you to just vote for what you think is right, and then we'll discuss what we know is actually happening. So I like bicycling, actually. I like tricycling, but it's easier to think about bicycling. So what causes the majority of air drag on a bicycle, including the rider? Is it pressure drag, shear drag, or so it turns out that it's pressure drag. Pressure drag is the big thing that cyclists are getting hit by, and it's about a big wake that is forming behind their body. And that's why the bicyclists try so hard to lean over and reduce the amount of area that they're projecting into the air, because the bigger their body area is that's going forward, the bigger the pressure drag is. Shear drag would be number 2. And then lift drag, I'm sorry, I just made that one up. It was just 2 technical words stuck together and it doesn't actually mean anything. So I apologize for being mean. Okay, so what did you learn from this? You're just, at this point, you're just like taking Monroe's word for it. Pressure drag is a whole lot more significant for a bicyclist than is shear drag. You have to have a very streamlined body before shear drag ends up being the more important thing. And our human bodies are not very streamlined. Perhaps if you were a dolphin, and I don't actually know the answer for a dolphin, dolphins are extremely streamlined, and it's perhaps, I don't know the answer, you could look this up, whether their drag is mostly, or whether what's slowing them down is mostly fluid pressure drag or shear drag. But for us on a bicycle, it's pressure drag. Okay, next poll. which orientation causes the most drag? These are all round discs. So just a round disc, maybe with smooth edges, and I'm holding, one of them is flat, one of them is like this, and then 3 and 4, they are hemispheres, so like a cupped hand, okay? And in one case, the cupped hand is like this, and the air is coming from this side, and in the other case, the cupped hand is like this, and the air is coming from this side, okay? And I want you to think about which do you think will have the most drag. You can assume that the diameters of all these guys are the same. Should there be an equation, or like, how can you look at this and just know which one is going to have the most drag? So let's talk about that. So I'm arguing that it's number 4 is the worst case scenario. And let's see why. So in order to understand this, we need to draw the streamlines that begin on the upstream side of the 2 cases that I'll compare. And it'll be clear why these 2 are interesting ones. The next in line is actually number 2. And I think that one had a good number of votes as well. So number 2 is quite bad. Number 4 is even worse. And then, should I put these in order? 4 is worst, 2 is next bad, 3 is next, and 1 is the best, having the lowest drag. Okay, so why? So if we draw the streamlines, our goal is to identify which of these objects produces the largest wake. And the wake is where the streamlines have separated from the body, and there's this turbulent wake. Think of traveling behind a tractor trailer going down the road. You're in that turbulent wake. So let's do some streamlines. So there's one streamline for this first hemisphere. And there's a streamline going into the center for the other hemisphere. And what you see is that this streamline it went into the hemisphere, it came back out of the hemisphere, and it had to do like a 180-degree bend to actually get going in the right direction again. See that? This part right here is what's critical. There was fluid that was coming out of the hemisphere that had to turn around and reverse direction. And you can't just do an instant change in direction. The F equals ma law makes that illegal. So you have to turn around slowly. And so that's what makes this extra little bend out here, and means that the streamline ends up being away from the body where it's separated. So if we would look at the dimensions of the wake, which is all the fluid in between the streamlines that are separated from the body, the wake for this second hemisphere is bigger than the wake for this first hemisphere. Are you on board with that? That makes sense? And it's because a streamline can't just take a sharp turn. It has to bend slowly. And then, okay, point number 3 here is which object has the lower pressure in the wake? And drag is caused by there being a low pressure, partially caused by there being a low pressure in the wake. And if the streamlines are bending hard at the point of separation, then the streamlines will be closer together, and that leads to some interesting consequences. So let's do the next slide. So I'm switching geometry here to a flat plate, and we have a flat plate, flows coming at it, and some of the streamlines are going, well, the streamlines are going around the plate, and you can see that there's flow separation. The flow separation, whoops. I have this problem that because I use Onshape a lot, I think that I should be able to zoom around and look at things at different angles just by moving my mouse in any application. And I just tried that in PowerPoint and it didn't work. Okay, so there's separation right at this point on the disk, and these streamlines get close together as they go around the edge of the object. And what happens if streamlines are getting close together? So we're going to take a point 1 and we're going to compare it with point 2, and we actually need to move. I should have moved point 1 up to a different streamline because I need to be on the same streamline. And if we apply, okay, first, we go back. First conclusion, V2 is greater than V1. How do I know that? Because at point 2, the streamlines are closer together. And so by mass conservation, if the same amount of fluid is traveling in between any two streamlines, so if the streamlines are closer together, that means that the velocity is higher. Are you good with that? The velocity is higher where the streamlines are closer together. So V2 is greater than V1. We're going to apply the Bernoulli equation here between point 1 and it's funny, I'm seeing this error in my notes. That point 1 ought to be up on this next streamline because Bernoulli equation has to be applied along a streamline. It doesn't change the conclusion here. So we have this equation from Bernoulli, and if we just change our geometry and say we're looking down on this plate, then point 1 and point 2 are both at the same elevation. So Z2 is equal to Z1. And that means, because the only other terms left are the velocity terms, if V2 is greater than V1, then P2 has to be less than P1. Are you fine with that conclusion? Because V2 was big, that means P2 has to be small to make the equation match. So P2 in the streamlines at the point of separation is low. And if you just travel a tiny bit across the streamline into the wake, your pressure is not going to change significantly. And so the pressure in the wake is also low. I don't know if you found that interesting or not, but it's kind of powerful. With very simple logic, we're able to show that the velocity at the point of separation is high, and that because of Bernoulli equation, that means that the pressure is low, and that means that the pressure in the wake is low. And what it tells us is anything that we could have done to make the streamlines further apart at the point of separation would have made the pressure in the wake higher and would have reduced the drag on the object. And there's a whole field of streamlining that is about doing precisely that. The pressure in the recirculation zone in the wake behind the object is relatively uniform because the velocities in that zone are relatively low. It's turbulent, yes, but the velocities are relatively low. And so the pressure is relatively constant across the entire back of this plate. And that's what's causing the majority of the drag. So the reason that the hemisphere that was pointed into the flow is so bad is because the streamlines are even closer together at this point of separation because the streamlines had to deflect even further. And we have a bigger wake. So we have two things that are bad, bigger wake and lower pressure. Okay, enough of that. Then let's, and I'll add even a third thing that makes it bad. This is just like for extra credit. There's flow curvature. The streamlines are curved at point 2. Streamlines are curved. And if a streamline is curved, think hurricane. As you move towards the center of curvature, you move towards lower pressure. That's another, actually, there's a completely different derivation of the Bernoulli equation that allows you to travel perpendicular to streamlines. And it's like the proof that hurricanes have low pressure in the middle. So that is yet a third reason why the pressure in this recirculation zone is low.